Hey everyone, continuing with the next question type, we have solving polynomials. And whatever we have known about polynomials, how to solve them, the theorems are still applicable here. So we have factor theorem, remainder theorem, they are still applicable here, even though we will be dealing with the complex numbers. However, in complex numbers, there's an additional theorem. It's a pretty simple one, and it's called the conjugate root theorem. Now, the conjugate root theorem states that if we have a polynomial with all real coefficients, so polynomial with all, keyword all, real coefficients, we will have conjugate solutions. Now, what do you mean by conjugate solutions? Let's say we have a plus bi as a solution. A is any number, any real number. B is any real number, which includes 0. If a plus by is a root, our solution a minus bi, the conjugate, is also a root. So even if you have real numbers, let's say 5, we know that, well, the imaginary part is 0, minus 0 is still 0, so 5 itself is a conjugate of 5. But if I were to have 1 plus I as a solution, then we have 1 minus I also as a root. Now, the main important thing is all the coefficients must be a real number. If you have at least one imaginary solution, or rather one imaginary coefficient, then the conjugate may not be a root. Now, keyword may not, it can be a root, but it is not guaranteed. So there might be some cases where the conjugate is also a root, but doesn't happen all the time. Whereas if we have all real coefficient, this happens 100% of the time. All right, and let's apply this in our two examples, where we first have a polynomial with all real coefficient. And we have a quartic polynomial, power 4, and it has the root of 1 plus 2i. And we need to find the value of alpha. So we don't know alpha is a complex number or not, but given that they want to find the value, it's likely a real number. So very simple, it has a root of 1 plus 2i. That means if we let fz equals to z power 4 minus alpha z cubed plus 10z minus 25, we know that f1 plus 2i would equal to 0. This is the factor theorem, or the remainder theorem. From here, we just need to substitute every z with 1 plus 2i. So we have 1 plus 2i power 4 minus alpha 1 plus 2i whole thing cubed plus 10 plus 20i. I'm just going to expand the 1 to z first because it's easy, minus 25 equals to 0. Now, you can use the GC to actually calculate all the complex numbers because, well, here they are all integers, so it's pretty easy for us to actually calculate this. If it's, let's say, a square root, then you need to expand it manually using the binomial theorem. So for 1 plus 2i whole thing power 4, we have minus 7 minus 24i. Then for 1 plus 2i cubed, we have minus 11 minus 2i. So I'm just going to combine the minus inside. I'll get plus 11 alpha plus 2 alpha I. Breaking this down, I get minus 15 plus 20i. Now, from here, what do we do? Because the whole thing has to be equal to 0, we will now split the imaginary and the real part. But you can just choose to only just check one part, because if one part checks out, the other part should also check out. So looking at the real part, we have 11 alpha minus 7 minus 15 equals to 0, alpha equals to 2, right? 7 plus 15 is 22, is on the other side, divided by 11 is 2. You can check your answer with the imaginary part as well. Imaginary part, we have 2 alpha minus 24i plus 20, which equals to 0. You notice that we bring this over, 24 minus 20 is 4, alpha equals to 2 as well. All right, so it all adds up, we know that the value of alpha is 2. And because alpha is 2, we have all real coefficients. And from here, we know that, hey, we can use the conjugate root theorem. Right? We now have 1 minus 2i as a solution. So very simple. Without using the GC, find the other roots of the equation in exact form. Okay, so we have, this is an important statement to write down. Since all coefficients are real, one minus 2i is a root. And now from here, we will then use the factor formula of, or rather not factor formula, we use a factor theorem. And I'm going to show you how how we could actually find the other factor just by inspection. But first of all, we know that we have two factors, z minus 1 minus 2i and z minus 1 plus 2i. So what I'm going to do is to expand this first to give us a quadratic factor. So it's easier for us to obtain the other quadratic factor when we break down the quartic equation. So clearly we have z squared. Then we have minus minus become plus. 1 minus 2i times 1 plus 2i. We know that that gives us a squared minus b squared. But of course here is a squared plus b squared. So 1 plus 4 because of the I squared becoming minus 1. Plus 5. Now, the coefficient of z of this quadratic factor. How do we find it? Very simple. Minus minus, so maybe minus. So we have minus 1 plus 2iz minus 1 minus 2iz. Alright, so we have minus 1z minus 2z. Minus 2iz plus 2iz giving us 0. So we have z squared minus 2z plus 5. So from the quartic equation, we have z power 4 minus 2z cubed plus 10z minus 25 equals to z squared minus 2z plus 5. This is the first quadratic factor. Now, the other quadratic factor, very simple. Power 4 coefficient is 1. So quadratic factor will have z squared only. Coefficient is 1. Plus 5 here is minus 5. So the constant here is minus 5. Alright, leave a gap. Now, we want to find the coefficient for z. So we have a minus z. Alright, why write a minus? Just in case it becomes plus, I can just simply add the plus sign. Now, we now look at either 10z or z cubed. Alright, looking at 10z, we know that this is only the way to obtain z. Minus 2z plus times minus 5 is already plus 10z, and we already hit our goal, which means that this is 0z. So actually what we need to do is simply z squared minus 5. The other roots, quite obvious, z equals to root 5 or z equals to minus root 5. And of course the other roots, we have z equals to 1 plus 2i, z equals to 1 minus 2i. Now we go on to hence, and this is a change to w minus 1. And I think it's quite obvious. Is it? Answer is no. Notice that here is minus, here becomes plus, here is minus, here it's actually plus. So first what you want to do is actually change the signs. W minus 1 holding power 4 plus, rather minus 2. When we change the sign, we get 1 minus w cubed. Similarly, plus 10, 1 minus w minus 25 equals to 0. Now we have all the signs right, and we have two z's that are substituted by 1 minus w, and one z that is seemingly substituted by w minus 1. But if you remember, because this is a even power, w minus 1 is the same as 1 minus w. So we just simply substitute 1 minus w with the z, and we get 1 minus w equals to plus minus root 5, or 1 minus w equals to 1 plus minus 2i. Now we just need to solve for w. Very simple. 1 plus minus root 5, or w equals to plus minus 2i. Alright, and these are the roots to the new quartic equation. Alright, so there we have it. Polynomials of real coefficients and how we can actually solve them using the same old techniques of factor theorem, remainder theorem, and the power of just breaking quartic down or factorizing by I power.